Last class, we reviewed a little bit about Bohr models, and we introduced the topic of orbital diagrams, which we said are just another way to represent an atom by specifically looking at the number of electrons. And we introduced this topic of a valence shell, or the place where valence electrons reside. And we talked about how there's this trend in the periodic table that the further you go down the periodic table, the more energy levels exist in an atom. The number of electrons that fit on each energy level, last time we said that the first energy level holds 2, and then every other one holds 8. We're going to backtrack on that second statement this time and recognize that this number is a little bit different because of this d block here. The d orbital is going to change the number of possible electrons inside of the electron shells, to where the first shell is still only going to hold 2. The second shell will hold 8, but the third shell can actually hold more than 8. And we'll discuss that in a little bit. But so we talked about the periodic trend of the further you go down, the further you go down, the higher the energy level, or the more energy levels there are in the atom. And today we're going to introduce that the further you go across on the periodic table, the greater number of valence electrons. That means the greater number of electrons in this valence shell. Specifically, we can count how many. Just like before, when we counted that the further you go down on the periodic table, the more energy levels. So the first energy level would correspond to the first row. Second row, 2 energy levels. Third row, 3 energy levels. Fourth row, 4 energy levels, etc. And now we're going to talk about how the valence shell, the number of valence electrons, can be determined with the number of the column number. So the first energy level, second energy level. We're going to skip this part right here, and we'll explain why later. But this one right here will have 3 valence electrons, then 4, 5, 6, 7, 8. So that is the number of valence electrons as we go across. And the valence electrons are just the electrons that reside in the outermost shell, or the valence shell. So we introduced the topic of orbital diagrams, and we talked about the different blocks, where the S block is on the first 2 columns on the far left. The P block is the last 6 columns on the far right. The D block is in the middle, and then the F block, those actually are located in here, and they extend the periodic table to make it a lot more wide. We're not going to deal a whole lot with the F block, but we do want to know that it holds 14 electrons. And we're going to specifically focus on the D block today. And again, an orbital diagram is just a way to specifically represent an atom's electrons, and electrons are represented by arrows. And I might draw my arrows a little bit weird, but they're just arrows, and they represent electrons. We did our orbital diagrams side by side with Bohr models, so that we can double check our answer and see that there's the correct number of electrons on each energy level. So here we have 2, and there's 2 here. Here we have 6, there's 6 here. Here is another example, silicon. And then now we're going to get into the new content. So again, we have our different orbitals, S, P, D, and F. And I'm going to go back on that statement on the maximum number of electrons in each shell. Before, I told us that the maximum number is 2 in the first shell and then 8 in every other shell. But that's because we were dealing with some more simple examples up in the top part of the periodic table. these top like 3 rows, and that was the case then. But once we get to this D block here, things are going to change a little bit, and that's what we're dealing with today. So there's actually a formula to determine the maximum number of electrons in each energy level, and that formula is represented by this equation here, 2n squared. And if you're not sure how to do the math on that, all you're doing is n is going to represent the energy level. So n is the energy level. So again, that is the row number on the periodic table. So first row is the first energy level. Second row, second energy level. Third row, third energy level, etc. And energy level is just the shell number. Number of shells away from the nucleus. So n squared is going to be, so like the first energy level, you plug in a 1 for n, and you get 1 squared times 2 equals 2. If you do the second energy level, 2 squared equals 4. It's just the number multiplied by itself. 2 squared equals 4 times 2 equals 8. And then the third energy level, 3 squared is 9 times 2 is 18, etc. And so the total maximum number of electrons that can possibly fit in each energy level is represented by the equation 2n squared. So I filled in these values over here on the left. Those are just what they'll end up calculating to be. But there's an important exception in that the last energy level, the outermost energy level, the valence shell, can never hold more than 8 electrons. So that is a hard rule, and there's exceptions to there. There's a lot of exceptions in chemistry. We're not going to learn about exceptions in this class. We're just going to deal with what the basics are. When you get to college, you can talk about exceptions. But the valence shell, the outermost shell, can never hold more than 8 electrons. So even though we might be on the 4th energy level, and we calculated the 4th energy level can possibly hold up to 32, if the 4th energy level is the outermost shell, it can only hold 8. So let's keep that in mind. The valence shell electrons are typically found in the s and p orbitals. So that's why before we were dealing with the d block, we just said the maximum they can hold is 8, because when we just look at the s and p blocks, we have 2 here plus 6 here, and we're never going to get more than 8. But once we start dealing with the d block, we're going to get more than 8 electrons in a shell, and I'll show you how that works and how we're never going to get more than 8 in that valence shell, because D does something pretty mysterious, pretty cool. So the valence electrons, again, we labeled our periodic table and said that there's a periodic table trend where we see that the first column represents that there's going to be 1 valence electron for those atoms. 2, 3, 4, 5, 6, 7, 8. And the goal is for every atom to get to 8. They're most happy with 8. And we'll talk about that later when we talk about periodic table trends. All right, let's do an example with orbital diagrams using the D block. So it's going to be a little bit more complicated than what we did last class, but it should be doable. I think we can do it. When we are doing orbital diagrams for anything with an atomic number greater than 20, so from 21 and on, I would recommend drawing the orbital diagram first and then drawing the Bohr model after. And you can use each other to double check each other's work, use each to double check each's work, but the orbital diagram is going to be easier to draw first. And I will show you why. So when drawing our orbital diagram, again, we're going to always start with our arrow pointed up, and we're going to label this as energy. Where down here is like where the nucleus is, and the higher up we go, the further we get from the nucleus. All right, so we're going to, just like last time, we're always going to start with our 1s orbital. But first, let's decide which atom we want to do. So let's do an example here with, we can do vanadium here and see what that looks like. So vanadium, we are going to start just like every other example with orbital diagrams. We're always going to start with 1s, and we're going to fill that in with as many electrons as it can hold until we get to the elements that we're at. So we're going to start with 1s, and that puts us right here on the periodic table. Cross off here, fill these two in, because we're going to fill this in with 2 electrons. We'll put electrons in green. Next, we're going to go a little bit further, and we see that, all right, check off as we go on the periodic table to help us keep track of things. All right, next, after 1s, we're always going from left to right. We are all the way to the right, so that means we're going to go down a row, and now we are on the second row, corresponding to the second energy level, and we are now in the S block. So we are going to draw here 2s, because second energy level, S block, and we will draw in our electrons, 1, 2, and check off where we're at. Again, we are doing the element vanadium here with an atomic number of 23. Let's do vanadium 51. The mass number won't really matter until we get to the Bohr model, but let's just have that written out so we know what so that we're extra organized. But vanadium, again, I said it has an atomic number of 23, which means it has 23 protons. We can calculate the neutron number later. It's not going to be important for the orbital diagram. But if there are 23 protons and it is uncharged, that tells us that there are 23 electrons. All right, so we drew our 1s and 2s. We got to see where we're at. We're moving from left to right. And we see that once we get here, we are still in the second row, corresponding to the second energy level. And we are now in the P block, P orbital. So when we're drawing these, I don't know if I've mentioned this yet, but we kind of have like these segments where we're going to draw things. So we draw the S orbitals in this column, and we draw the P over here, then the D over here, and the F over here. So you can kind of keep that in mind. And again, we're always drawing with higher energy corresponds to drawing them located higher up. All right, so 2s, after 2s, we've got 2p. So we're going to draw p. It's still in the same energy level as the 2s. It's still 2, but now it is located, it's located still slightly higher because it got filled in later. All right, and we're going to label this 2p. We drew 3 boxes because if we count, there are the p block is 6 atoms wide, meaning it is 6 electrons wide. And since each box holds 2 electrons, we want 3 boxes so that can hold a maximum of 6. And don't forget that our electrons like to be socially distanced. So we are always going to fill up 1 box with 1 electron each before any boxes get 2 electrons. And I did not mean to click on that. So each box gets its own before any box gets a second one. All right, so we just filled in our 2p. Next, we're moving left to right. We got all the way right, so we're going to move down a row, and we are on the 3s orbital. So let's draw it in our s column, and it's going to be a higher energy level than the 2s and 2p. We're going to write 3s. We're going to fill in our electrons. Let's check where we're at on the periodic table. Fill in here and here. So this orbital is going to be completely full. After 3s, I'm sorry, we're going to move left to right, and we get to 3p. So we will draw in 3p. And again, it's located a little bit higher than the 3s, but it's not way up here. It's still the same energy level. It just got filled after 3s, so therefore it's located slightly higher than 3s. So we're going to write 3p, and we're going to fill in our electrons. They're socially distanced at first, but then it's too crowded, so they got to put 2 per box. All right, so we'll check off where we're at on the periodic table. And we're moving left to right. We just filled up the 3p, so we've got to go down to the 4s. Fill that in next. Before I keep going with filling in my electrons, I'm just going to draw in some of the other orbitals. I can draw in as many orbitals as I want. They still exist, whether I draw them or not. So I'm just going to draw these to begin with and then explain what's going on after. So we're going to have our 4s orbital right here. And we will have, after 4s, there's going to be a 3d orbital that's going to be up here. And that's going to confuse some of us that it's the 3d orbital, but it's located higher. But no worries. And I'm going to draw this little platform here because something strange is going to happen here in a little bit. But what's going on here is we've got the 4s is going to fill before 3d, because if we look at where we're at on the periodic table, we're always filling in from left to right. So the 4s is going to fill in here before we get to this right here. But why do we call it the 3D orbital? I will get to that in just 1 second. So first, let's fill in the 4s orbital. We've got an arrow up, an arrow down, and we'll check off where we're at on the periodic table. Now this 3D orbital, sorry, let me actually draw it in. And we said this is 3D. And we have this little platform here because what happens is this is actually like a haunted house kind of thing. And we have this 4s orbital, and it is located at a lower energy level than the 3D orbital. And that's why it gets filled in first, because we always fill from lowest energy level to highest energy level. But what happens is when we fill in this 4s orbital, it acts as like a trapdoor mechanism to where we just unlocked this trapdoor and the 3D orbital falls down. And when it falls down to where it is now at a lower energy level than the 4s, to where it is now in the 3rd energy level, so that we are not, it is now in the 3rd energy level, so that we don't confuse things with our Bohr model when we're drawing things. But we've got the 3D and the 3rd energy level, but for whatever reason, the 4s gets filled first, and by doing so, it unlocks a mechanism to where the 3D orbital is going to fall, and then it will fill in at a lower energy level than the 4s. If that is extremely confusing for us, I'm not going to test you and say, does the 3D orbital fall down or does it stay where it's at? that doesn't matter. That's just a way to remember this. If you want to just remember it as an exception, you can do that too. You can just say, hey, the 4s is located higher than the 3d, but it gets filled in first because we're always going from left to right. If you want to just remember it like that, then that's fine. But as long as when you fill in the electrons on the 3d orbital, as long as you have the 3d orbital located below the 4s orbital, then you will get the question right. So the 3d orbital, we need to fill in our electrons. We have 1, 2, 3 electrons we need to fill in. 1, 2, 3 electrons that go there. So again, the 3d orbital is kind of strange. It's located on the 4th energy level, but it fills in electrons on the third energy level, but it's located on the 4th row of the periodic table. So kind of weird. And in our next example, we're going to explain that pretty well to make more sense of that. So we have vanadium 51, and we just drew the orbital diagram for it. Let me put a little note here so that we can remember that the 3d orbital it falls below the 4s orbital after the 4s orbital gets filled. So 3d orbital falls below the 4s orbital after the 4s orbital gets filled, and then the 3d orbital starts filling up. All right, let me make this a little bit smaller so that I have room to draw our Bohr model next to this. And I'll make this a little bit bigger so that we can read it. All right, so we'll now draw our Bohr model after this, and I'll show you why. It'll make a little bit more sense why we did it after. First of all, let's calculate the number of neutrons that vanadium 51 has. So it will have, let's see, 28. Yeah, 28 neutrons for over here. 28 neutrons, because 23 plus 28 equals 51. So we will draw in our protons. We've got 23 protons. We have 28 neutrons. And then first energy level. Second energy level. And you can actually go ahead and just count how many energy levels there will be and just draw them all at once at first. So I can count, and I see that vanadium is located on the 4th row of the periodic table. So therefore, it will have 4 energy levels. So I'll just draw all 4 of these to begin with. All right, now I'm going to fill in my electrons. and I'm just going to be referring to my orbital diagram to fill in the electrons. So the first energy level, we all know that that one holds a maximum of 2 electrons. The second energy level holds a maximum of 8. The third energy level, it actually holds 2n squared. It holds a maximum of 18. Let's count how many we have here to see how many we're going to be drawing in on this Bohr model. So I have, I'm counting my orbital diagram arrows. On the third energy level here, we're going to count how many electrons there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 electrons on the third energy level. And that's why I had us draw the orbital diagram first, because it's kind of hard to see the number of electrons that go on the Bohr model here when the before drawing the orbital diagram. The orbital diagram will help us see that there are 11 electrons in the third energy level. And then lastly, we're going to count how many are in the fourth energy level. And the fourth energy level here only just has 2 electrons. So we're going to draw 2 electrons. So we can tally up our electrons, and we see that the first energy level 1, first energy level, has 2 electrons, and the first energy level here has 2 electrons. The second energy level has 8 electrons. See, the 2's corresponds to the second energy level, and here we have 8 electrons on the second energy level. Let's look at the third energy level. The third energy level we have a total of 11 arrows drawn, and I have 11 electrons drawn on my third energy level here. And then lastly, let's look at our fourth energy level, and I have 2 electrons drawn there and 2 electrons in my fourth energy level on the Bohr model. And at the beginning of this video, I told us that the s and the p orbitals are going to represent the valence electrons, which is exactly what happened here. The d orbital is going to represent electrons that are not in the valence shell, typically. So that's why there are 2 electrons in the valence shell, because we had 2 electrons on this fourth energy level on the valence energy level, the valence shell. Whereas the d orbital, those got shifted down to the energy level below it, because there's a reason for it, and that's because we can't have more than 8 on the valence shell. But you might say, hey, wait a second. If these 3 electrons here were located on the outer shell, we'd still only have 5. And that's a really good point. But I will show you in this next example that we'll do why the d orbital always has to shift down, so that we don't end up with more than 8 on the valence shell. So let's do another example. Let me make another copy of this. All right, so we just did our example of vanadium 51. Now I want to do an example with an element located like over here. So let's try bromine let's try bromine 80. So I'm going to skip a slide and then I'm going to come back. Or I'll skip 2 slides, then I'll come back. So don't get lost on where we're at. Maybe I can reorder these later or something. But we said we're going to do the example bromine 80. And so this is going to help reaffirm why the d orbital has to shift energy levels so that we don't end up with more than 8 valence electrons in the outermost shell. So we said we were going to do bromine 80. And whenever we're doing whenever we're doing orbital diagrams located with anything here or over or down, it's going to be easiest to draw the orbital diagram first. So anything with an atomic number greater than 20. So bromine 80, it has an atomic number of 35. So therefore, it will have 35 protons. We're doing bromine here. So 35 protons. And then it has 45 neutrons. And it has 35 electrons. All right. The electron number is going to be what's important for this orbital diagram. And this orbital diagram is represented by an arrow up with, we're going to label our axis that says, and it's labeled as energy, our energy axis. All right. And next we are going to start drawing in our orbitals. So we always start with the s orbital, the 1s orbital. 1s, and I could even draw them all in now if I wanted to, but I like to usually just pause where we're at each time, but that is your preference. So the first energy level I'm going to fill in here and here, so that means I'm good to add the electrons in. Second energy level, we'll see where we're at. We are moving left to right, so we're going to draw in the 2s orbital. If you haven't caught the trend, you're always going in order of 1s to 2s to 2p to 3s to 3p to 4s to 3d to 4p, etc. To clear up any confusion on why we don't have a 1p, if we look on the first energy level, there's no p orbital here. P doesn't start until we get to the second energy level. Anyway, we are now at the 2s orbital. So we're in the second energy level, s block, fill in the electrons there. Next, we are moving on left to right. And we are in the p orbital. Sorry. So we're in the 2p orbital. We're going to fill in our electrons. So 1, 2, 3, 4, 5, 6. We're still not at bromine, so that means we're going to add in our electrons here. Next, we are going to go left to right. We're now at the 3s orbital. We can fill in our electrons. We're still not at bromine. And then after that, we're going to get to the 3p orbital. And then we're going to label it 3p, fill in our electrons. All right, we are still not at bromine. So we're going to keep going. We're going to fill in our, after After 3p, we're going to be here. So that is 4s. So we're going to fill those in. So 4s. And we can draw in our the next orbitals as well. So after 4s, we'll have 3d will be located up here. So we have, again, the 3d is located above the 4s. It's going to move in a little bit. And then we have the located a little bit higher than 4s, but lower than the, actually it's higher than the 4s and higher than the 3d. We have the 4p. It's going to be up here. All right, so the 4s is going to get filled in. Check off where we're at on the periodic table, so we can add 2 electrons there. And then boom, the 4s just got filled in. So now that causes the 3d orbital to shift down. So let's draw that 3d orbital shifted down. So the 3d orbital is now shifted down, and it is now located there. So the 4s, we unlocked our trapdoor, and the 3d orbital fell down. So the 3d orbital is now located there. We're going to fill in how many electrons are going to end up going there. So let's count. So let's keep going until we get to bromine. So put here 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 10. And we're still not at bromine. That means the 3d orbital gets completely filled. All right, 3d orbital is now completely filled. And we are now moving on. We're going from left to right, as always. And we are now in the p orbital, the fourth energy level, p orbital. And let's see how many electrons we need to fill in here. So the p orbital, located above the 4s, 4p, and sorry, let's count how many electrons we need to go over, because we're going to stop once we get to bromine. 1, 2, 3, 4, 5. So fill in 1, 2, 3, 4, 5. We stopped at bromine, so we have 5 electrons in the 4p orbital, and that is our completed orbital diagram for bromine. So this is the orbital diagram for bromine. This is what it's always going to look like. Let me make this smaller so that I can draw my Bohr model and emphasize a point about the d orbital. All right, so hopefully I think that'll be enough room to draw our Bohr model here. So the Bohr model, we're always going to start with the number of protons and neutrons in the center. We calculated that there are 35 protons and there are 45 neutrons, all inside of a nucleus here. And then we have our first energy level. We have our second energy level. And how many energy levels do we have total? Well, we're going to see that bromine is located on the 4th energy level. 4th row of the periodic table corresponding to the 4th energy level, so there are 4 total energy levels. right, third energy level, and then here's the fourth energy level. All right, fourth energy level drawn in. All right, how many electrons go on each energy level? All we're going to do is we're going to find the energy level on the periodic table, and we will count how many electrons are there. So the first energy level, we have 2 arrows, meaning that there are 2 electrons in the first energy level. The second energy level, we're going to count how many electrons are in the second energy level. So we have 8 electrons in that second energy level. Next, we have the third energy level. And if we count all of those electrons, we're going to get 18 electrons in the third energy level. 18 electrons in the third energy level. And then on the fourth energy level, we're going to count how many electrons we have. And if we count all those, we're going to find that there are 7 electrons on the fourth energy level. So our question before of, wait, why do the electrons in the d orbital, if the d orbital is located on the fourth energy level, then why am I drawing the electrons in on the third energy level? Well, the d orbital, it has to shift down so that we don't end up with more than 8 electrons here. Because if all of these electrons from the d orbital ended up going to the outermost shell, if they ended up going to the fourth energy level, since the d is located on the fourth energy level, or on the fourth row of the periodic table, if they ended up going to the fourth energy level on our Bohr model here, we're going to have way more than 8 electrons on that outermost shell, and we can't have more than 8. There's a couple of exceptions, but there's never an exception where you're going to have like 20 or however many that'll add up to. So the d orbital always has to shift down so that we'll never end up with more than 8 electrons in that valence shell. So that is the reasoning why that d orbital has to shift down. And then let's double check our work on this Bohr model by comparing it side by side to our orbital diagram here. And so I have our first energy level. One is going to have 2 electrons. We have 2 electrons here. Our second energy level has a total of 8 electrons. We have 8 electrons in the second energy level. Our third energy level has, we can count all these arrows, feel free to count them. We have 18 electrons in this third energy level. And then our last energy level, our fourth energy level here, has 1, 2, 3, 4, 5, 6, 7 electrons drawn. We can also count the total number of electrons, and we see that we calculated there should be 35 electrons. There are 35 arrows drawn here, and there are 35, if we add up 2 plus 8 plus 18 plus 7, we're going to get 32 electrons drawn, or sorry, 35. So there are 35 electrons drawn here, and if we add up 2 plus 8 plus 18 plus 7, we're going to get 35 electrons drawn there on the Bohr model. So there's another more complicated example for us. Expect that we should know how to draw Bohr models for any element up to, let's say, we should be able to draw Bohr models for any element up to here. up to barium, I believe that is. So just FYI. Next, I want to... Actually, we are going to end here, and then in my next video, I'm going to explain how to do electron configuration, and that'll be a really quick video and really quick concept. But hopefully that helps clear up any confusion and help to expand in our understanding of how to draw orbital diagrams.